This video is about hypothesis testing. Hypothesis testing is an important tool in medical research, and it's also fair game for your boards. So in medical research, we're often trying to compare two groups. For example, say I want to study a new blood pressure medicine. One way that I could do this would be to get a group of people and give them the study drug, and get another group of people and give them a placebo, and then compare the average blood pressure between the two groups. So the question that I'm asking is group 1 equal to group 2? Or are they different? So these comparisons can be a little bit tricky because sometimes groups are different just by luck of the draw. So just due to random chance, I might pick a group of people for group 1 who has a lower average blood pressure than the people in group 2. The question in statistics then becomes, if there's a difference between the two groups, is it just due to random chance? And so the way that we go about addressing this is with hypothesis testing. We're going to start with a hypothesis that most researchers secretly hope to be true, which is that group 1 does not equal group 2. Researchers want this because they usually want to show that there's a difference between the groups. They want to show that the people who got the study drug have a different outcome, have better blood pressure than the people who did not. So the way that we test this is with another statement that we hope to prove false, which is that group 1 equals group 2. They are the same. They have the same outcome. And this is referred to as the null hypothesis, which is written with a big H and a little subscript 0. You can think of the 0 as being for zero difference between the two groups. And this, the first statement, the one that researchers are usually secretly hoping for, this is the alternative hypothesis. This is what we want. This is what we test. And something that I want you to notice is that these two statements are mutually exclusive. That means if one of them is true, the other one is false. They cannot both be true. Now that we have our null hypothesis, we need to decide whether or not we think that it's true. If we think that it is not true, that is called rejecting the null hypothesis. And the way that we decide whether or not to reject the null hypothesis is with something called a p-value. The p-value is calculated using our data. So we plug our data into some statistical software and out comes a p-value. And if the p-value is small, that means that we get to reject the null hypothesis. We're betting that this is not true. We're betting that this is true, that there is a difference between the two groups. So when p is small, we get to reject the null. If instead p is large, we fail to reject the null hypothesis. We're stuck with it. We have to say that the groups are not different. So smaller is better for p-values if you're trying to show that groups are different. So how do we decide what counts as small? The way that we do this is with something called alpha, which is the significance level. And by convention in biomedical research, this is set to 0.05. This means that we are willing to accept up to a 5% chance that the difference between the two groups is due to chance alone. So we're willing to accept up to a 5% chance that the difference that we observe between the two groups is not due to the study drug, but actually due to just random chance. So alpha is the cutoff level where we decide whether p is small or large. If p is less than alpha, if it is smaller than 0.05, that means that we get to reject the null. And if p is greater than alpha, that means we fail to reject. So when p, like I said, is less than alpha, that means that we have reached statistical significance. This is what people are going for when they do research. And the way that this is denoted sometimes is with a little star. So we'll give this p a star. Researchers are always running around trying to get the smallest p possible. Remember that a smaller p is better if you're trying to show that there's a difference between groups. And if you're having a hard time getting that to stick in your head, remember that in statistics, a small p makes a big difference. Okay, so far we've been talking about rejecting the null or failing to reject the null based on our data. We calculate p and we compare it to the preset alpha, and we're trying to make a decision. We're making a guess, and this is a little bit weird to think about, but since we've been making a guess, that means it's possible that we're wrong. We could be guessing that the groups are the same when the reality is that they're different, or vice versa. And if we're guessing wrong, we're making an error. There are two types of error that you need to know about. Let's just talk about them with a table. On the top of our table, we'll talk about the truth about the null hypothesis. So the null hypothesis can either be true or it can be false. This is the reality. This is what we don't necessarily know. This is what we're guessing at. So on the side, we're going to put our guess. And the guess that we make is based on our hypothesis testing. So if we do our hypothesis testing and we get a large P, we fail to reject the null. And what that means is that we are guessing that the null is true. T for true. And if we get instead a small p and we reject the null hypothesis, what we are doing is we are guessing that the null is false. Okay, so let's start in the universe where the null hypothesis is in reality true. Regardless of what our data actually tell us, the null hypothesis is true. There actually is no difference between them. If we use our data to guess that the null is true, we're correct. We made the right decision. If instead we guess that the null hypothesis is false, still in the universe where the null hypothesis is in reality true, we have made an error. This is called type 1 error. Type 1 error is rejecting the null hypothesis even though it's true. The probability of committing this type of error is equal to alpha. It's actually the same alpha as here. So if this is alpha, the probability of this is 1 minus alpha. All right, let's move on to the universe where, regardless of what our data end up telling us, the null hypothesis is false. There actually is a difference between the two groups. If within this universe where the null hypothesis is false, we make a guess that the null hypothesis is true, we have again committed error. We've committed a type 2 error. And the probability of committing a type 2 error is equal to beta. All right, and if in this reality where the null hypothesis is false, we guess that the null hypothesis is false, we're correct again. And this is equal to 1 minus beta. And this actually has a name. This 1 minus beta, or the probability of guessing that the null is false when it actually is false, this is referred to as statistical power. Power is a good thing. We want it to be high. It's actually an indicator of the likelihood that we're going to make the right decision here. So the thing that I want you to remember about power is that it increases with larger sample sizes. So a bigger study with more people means greater statistical power. All right, so to recap, hypothesis testing is how we decide whether or not two groups are different, and we do that by comparing a p-value, which we calculate from our data, to alpha. If p is less than alpha, we reject the null hypothesis. And if it is larger than alpha, we fail to reject the null hypothesis. If we reject the null hypothesis when it is actually true, we have committed a type 1 error. And if we fail to reject the null hypothesis when it is actually false, we have committed a type 2 error. And finally, power increases with increasing sample size. And that is hypothesis testing.